Hello everyone, and welcome to our presentation of the Pendulum Tune Mass Damper for floor vibration control. We are Hugo Chen and Niels Hofmeijer. Let's talk about underside vibration. In engineering, it's very important to estimate vibration through structures. Engineers should always avoid excessive vibration through structures at all costs. An example is here the Millennium Bridge in London in 2000. It was closed after 2 days of its opening because of excessive vibration induced by the people walking over the bridge. So how do we control vibration? We have two ways to control it: active control and passive control. In active control, sensors sense the vibration and direct actuators to oppose the vibration. In passive control, you have a mechanical system that works 24/7, and the advantages are that it is low cost and low maintenance. It's often in the form of a tune mass damper. And there are two types of tune mass dampers: a translational tune mass damper and a pendulum tuned mass damper. For example, the one used in Type A 101 on the right side. You can see both tune mass dampers on the bottom left figure over here. When the structure starts vibrating due to an earthquake or wind, the pendulum will pull onto the structure, opposing the vibration due to the inertia of the mass of the damper. Imagine that the mass of the damper in Type A 101 is 660 metric tons. And the problem statement of our project is going to be: how can a tall building with a pendulum tune mass damper like Type A 101 be modeled? And what is the influence of the pendulum's mass on the vibration throughout the building? For this project, we will consider a 20-story building. There are several technical challenges. One is that multi-degree of freedom switches are hard to solve. We use MATLAB to solve these matrices. Then it's also difficult to estimate the damping between the floors, and we use Rayleigh damping for this, which we will explain in a couple slides. First, we consider an undamped case, a 2 degree of freedom, and we can solve this by a direct method and by drawing the free body diagram. This gives us the equation of motion, which is shown here on the bottom left figure. And with assuming that the damper mass is very large and that there are small angles, it can be put in the form of in the matrix form over here. Then let's assume that the response is going to be in the form mentioned on the top left side. And when we take the second derivative of it, we can put it back into matrix form, and the matrix form will turn into this form mentioned on the bottom left. And this is going to be an eigenvalue problem, where lambda is going to be omega squared, which is the natural frequency squared. With these eigenvalues, we can plug them back into the eigenvalue problem, into the characteristic equation, and obtain the eigenvectors. Then the response can be solved as shown over here. Now, with damped vibration in real life, a building will always have damping between floors. So the model is going to change to this. The direct method can be used again, but now the eigenvalue problem, lambda, will be a complex number, with omega d being the damping frequency, which is the natural frequency times the square root of 1 minus the damping ratio squared. But now these damping constants are very hard to estimate throughout the building. So therefore, we use a Rayleigh damping. Rayleigh damping model assumes that the damping is proportional to the mass and stiffness. But how do we get these coefficients for the mass and the coefficient for the stiffness? Previous studies show that earthquake-induced vibration through buildings, the damping behavior is only stiffness proportional. That means that the mass coefficient is 0. A visualization of Rayleigh damping is shown here on the right figure, with on the left side the stiffness proportional damping, which will be used in this problem. Then we use a modal analysis to solve the problem. And model analysis starts with assuming the response to be a time function times the normalized model matrix. Putting this into the matrix form and multiplying that matrix form times the transpose of this normalized model matrix will result in this equation, where since it's normalized to the mass, it will turn into an identity matrix. Since the stiffness divided by the mass is the omega square, this equation, no, this term will turn into omega squared times the identity matrix. Then the middle term can be used for Rayleigh damping, and we can write it out as this, and it becomes this term right over here. Now plugging that into the equation of motion, we get this equation of motion. Since this term is equal to 2 times the mass times zeta, we can calculate zeta for each floor. To solve the equation of motion, we use Duhamel integral, and we end up with this equation over here. So in the figure on the right, we can estimate the zeta value for the first mode according to the height tall steel buildings. And in the worst case, this zeta is 0.01. With CK, all the zeta values can be obtained for each floor. And in our project, we use a 20-story building, so all the matrices, the stiffness, the mass, the damping, will be 20 times 20 matrices, and can be solved using the same procedure as shown before by the model analysis. Now let's talk about the results.
Here are the results of our project and investigation into pendulum mass. Looking at the short-term effects of different pendulum mass, we first set a baseline condition, which is 20-story building, a level 7 earthquake, which is 0.3 meter per second ground speed, velocity, and 0 initial displacement, and looking at the 0 second to 100 second response of the building. Using those conditions, we generated 2 response plots using a pendulum mass of 10 and a pendulum mass of 10,000. We see that the larger pendulum mass created a larger first negative direction response, but at a later point in time. Looking at the long-term effects of pendulum mass, we use the same basic condition as the short-term effect, but lengthen the response plot to 0 second to 1000 second. After some time, both buildings observed to have similar response where the building converged to somewhat of a steady state like condition. But looking at the left side of the plot, we see that the larger pendulum mass reduces the number of large oscillations and actually lengthens the time between the peaks. And the smaller pendulum mass has more oscillations, but at a lower amplitude compared to the larger pendulum mass. One of the interests of the project was to determine the best pendulum mass for our starting condition. We plotted the max amplitude of the building after the initial event against the pendulum mass and created a plot shown on the right. The best pendulum mass for our building was determined to be 545, which created a max amplitude of 0.169. Comparing that to a no pendulum condition, it reduced the max amplitude by 26%. Concluding on our project, we created a MATLAB model of a simplified building system to analyze the effects of a pendulum mechanism on building response after such an event. For our earthquake situation, we determined that a larger mass produce a larger first negative amplitude, direction amplitude, but at a later point of time. And a larger pendulum mass reduce the number of large oscillation and the time between peaks in terms of long-term effects. The best pendulum mass for our conditions were found to be 545 and created a 26% decrease in max amplitude compared to no pendulum. In terms of broader impact, others could use our model to see if a pendulum mechanism could improve their system response. And future improvement of the project could be that we could look into the effects of pendulum length and how that would change a building response. Here are the references used for our project. Here's the table of earthquake magnitudes and ground velocity. Thank you for listening to our presentation.